Angshu, my screen is visible to you? Angshu,
Yes, sir, it's visible.
Sarka slide, is it visible?
Yes, sir,
Okay. Available with us, I can start now.
okay, sir. Okay. So we'll now begin technical section 2 of the day. And we are truly honored to have with us Professor Vikas Pal, sir, from Imperial College London, who will be delivering today's session. A very warm welcome to you, sir. So before we begin, I would like to take a few moments to introduce our esteemed resource person. He is a professor of power system at Imperial College London and is recognized globally for his work in power system stability, control, and estimation. He received his foundational training in electrical engineering at Jadavpur University, pursued advanced graduate studies in power engineering at the Indian Institute of Science in Bangalore, and culminated his academic formation with a doctoral degree from Imperial College London, supported by the prestigious Commonwealth Scholarship. Professor Pal has led major UK-China and UK-India collaborative research programs on renewable energy integration and system control, and collaborates extensively with leading industrial organizations including ABB, Siemens, GE Grid Solutions, and National Grid UK. His research has contributed to industry-supported innovations such as fast power flow and volt-VR control tools, which are now integrated into Siemens Spectrum power platforms and used by utilities worldwide, as well as HVDC interaction models for large-scale wind farms in partnership with GE. Professor Pal has published around 140 IEEE transaction papers, authored 4 books, and has been honored with several prestigious recognitions, including Fellow of IEEE for contributions to power system control, Fellow of the IET and Chinese Society of Electrical Engineers, Fellow of the Royal Academy of Engineering in 2023, Prabha Kundu Power System Dynamics and Control Award, and elected to the Chinese Academy of Engineering and the Indian National Academy of Engineering in 2025. He is also an IEEE distinguished lecturer, former editor-in-chief of IEEE Transactions on Sustainable Energy and IT Generation, Transmission and Distribution, and currently serves as IEEE PES President, elect for the presidency term 2028-29. We are honored to have him with us today. So I would like to request sir to take over the session. Thank you.
Thank you, Angshu. Very kind introduction. So let me share the slide. Are you able to hear me?
Yes, sir, you're audible.
Share the screen. What I get? Can you see this slide with the
Yes, sir.
title?
Sir, it's coming. Yes, it's visible.
Okay. Now I go to the slideshow mode. Let's see if it. Slideshow mode is somehow not going to that. Oh, okay. Now it is coming. Pointer of some. Okay. So this is the topic. Why I said journey rather than destination is actually that I always enjoy the journey more than the destination. And this journey has been mainly the research in power transmission control, power distribution, volt control, and then also the estimation, dynamic state estimation, which is different from the robust control. The talk overview, robust control, then robust estimation, and then application, and then I'd like to show you the researchers who also work with me in this topic. If you don't understand, you can always, speak and interrupt me. That would be good. So the power transmission, the challenge is the scale and complexity. If you look at this country like Brazil, that from north to extreme south, where it is bordering with Paraguay, Bolivia, Uruguay on the south, and then in the north, it is Amazon. The whole distance is 3,900 kilometers. Now, if you have extra high voltage or ultra high voltage transmission systems, which they have to have because it's a long distance, so then transmitting power is not that easy. And on the right hand side, you could see that that's the whole of the European peninsula, starting from northern Norway to southern Spain. So that's the size of a country like Brazil, where power transmission is a challenge. So this is what I'm showing it, and then that would set the context for the robust control and oscillations and so on. So what are the limits in AC power transmission? Now we are talking about so much of renewable, solar, wind and all, but that's all in the generation end. Transmission system is going to remain AC. So would be the distribution. So that means their characteristics will remain.
दूसरे क्यों निकल रहा है?
Sir, you are not audible.
सर्वर
I don't know what happened here. Hello?
Yes, sir. Now it's fine. You're audible now.
You're
Sorry.
audible,
No,
right?
I have. Yes or no?
Yes, sir.
Yes,
Now
yes.
you're audible. Yeah.
Okay. So, but it should not be a problem. It's a hotel in Beijing. It's a good internet. So 1100 kV, typically in a large country like say China, where I am now today. So they have this natural loading. You see that surge impedance loading, which is 5,500 megawatt. Now let's talk a little bit about the surge impedance loading concept. So what is a surge impedance loading or natural loading? Natural loading is that the loading at which the voltage across the entire transmission line length remain flat. So sending end voltage, if it is 275 kV or 400 kV, receiving end voltage also will be 400 kV, provided the line is loaded by this natural loading. So what happens? So it is that value of the loading or the load current, which when passed through the transmission circuit, that transmission circuit has got series inductance, and also transmission conductors are insulated with respect to the ground. So they have line to ground shunt capacitance. Now, because this capacitance is charged with the voltage, transmission voltage of say 400 by root 3, so there would be omega C V square, that reactive power that will be generated. And because the line also is carrying current I, and if the XL is the inductive reactance, So that line also would be absorbing I square XL amount of reactive power. So if we fix the length, say per unit length, say per kilometer, when in per kilometer I square XL is equal to omega C V square. So what is happening is the line itself is generating a capacitive var, which that is being absorbed exactly by the inductive circuit element in this transmission line. So that means there is no net var generation or absorption. And as we know, if there is no net var flow through a transmission conductor, so there is no voltage difference created. So that's why the voltage profile remains flat. But what is going to happen is the receiving end voltage phase angle will differ from the sending end voltage phase angle. So that is called surge impedance loading, but that's very rare that one can load this. Now, what are the other thing in the second row? Thermal rating or normal condition. So this is for 275 kV, it's about 500. For 400 kV, it is 1500. And again, for 765 kV, it is 5500. And 1100 kV, it is 24,000. But it is not exactly going to be like that. That depends on the conductor geometry. How many conductors you have, conductor spacing, and then inductance, and then the capacitance, because all these things lead to that V square by 1 by root LC value. So 250, 500, 2200, 5500 is just like a sample one. The thermal one, essentially what happens? So you have the conductor, these conductors are carrying current, so they will have an expansion. But then because of the expansion, they will have a sag. And when there is a sag, there would be, of course, change of the clearance. But particularly when these conductors are connected at the substation, the first, when the conductors are starting, so in the first tower, there would be this some kind of support, so from which this conductor will start. And now when the conductor is heating up, so that end would expand, and because of that, when the annealing temperature of aluminum is reached 130 degrees Celsius, so that is the limit. That is the limit beyond which you cannot carry current, because at that point the conductivity of that transmission conductor would permanently change, and then so that is called thermal limit. So now in reality, are we able to reach thermal limit? We can reach or exploit thermal limit depending on the length of the line. If the line is less than 50 miles, then thermal limit is possible. Reaching that thermal capacity is possible. If the line is between 50 to 80 miles, or if the line is say up to 80 miles, then okay, so between 50 to up to 50 miles you can do this. So then between 50 to about 200 mile lengths, the voltage stability will actually start having the constraint. This is the voltage constraint that is particularly if you carry more power than surge impedance loading, then what happens? More than surge impedance loading means the current in the line is large. If the current in the line is large, I square XL is more and omega C V square is less. So there is a net absorption. So that reactive power there is no balance of the reactive power between the capacitance and the reactance. So this more reactive power has to come from the sending end. And when the reactive power travels, that need a voltage gradient. So that's a voltage issue. So the longer actually up to this, then there is a voltage stability. And beyond that, what happens is when the line is between 200 kilometers to higher, that is, 200 miles means 320 kilometers. 320 kilometers and up, there the voltage stability will not be issue. The issue would be angle stability. And it will be far less than the surge impedance loading. Why the angle stability? Because the line length is long. So for every kilometer, there will be an angle difference. So you have large angle difference. And with the large angle difference, so your angle stability in the power angle curve, you move towards the, peak value of the power angle curve. So these are the constraint for power transmission in the AC line. And then when angle stability or voltage stability manifest, what is the nature of that manifestation? The nature of the manifestation is oscillation in the power line. How that oscillation comes? If there is a small disturbance, more change in load, so that load change will lead to the power oscillation in the line. What is this power oscillation? See, we are talking about RMS power megawatt. So that is VI cos phi. V is the RMS value, I is the RMS value, cos phi is a number. So where we get this oscillation? This oscillation is very low frequency oscillation, less than 2 Hz. So this is sometimes called inter-area mode. Or if the oscillation is within the power plant complex, then that is called intra-plant mode. Or if the oscillation is between the generator itself and the rest of the network, then that is called local mode. But we are not going to the local mode or intra-plant mode because that is within the power plant complex. Let's go into the inter-area mode because we are talking about long distance transmission. So what is this inter-area oscillations? Inter-area oscillations like the generators in one power plant, when there is a small disturbance or change in the power flow, would have electromechanical oscillation, and they would oscillate with the other generators in other locations. So the location that you are in, say Durgapur, so there are a couple of power plants there. There are also Shataldi. There is also Durgapur, the DVC, the TPL. Then also bit north, you have the Farakka, and also you have the power plant in Birbhum. So that these things, if I take, so they become the power generator cluster in West Bengal, some of them. Okay. So, and then Bankura, Mejia and all, so they become one cluster. Now these powers are getting transferred towards northeast, towards the northwest Delhi area. So then there are, that side also there are many super thermal power plant, the NTPC, Talcher, Korba, and all these things. So now in these lines, there will be oscillations. So there are 400 kV lines. Typically, you could be able to observe those oscillations if there is a analog power meter. So this oscillation is essentially a pathway to blackout. So then what is the nature of the oscillation? One can conceptualize that all the power plants that I just named, this in Tilpara or Durgapur or Farakka, and then on the other side, Korba and also Rajasthan and Uchahar in Uttar Pradesh. There are many these. So between them, there is a transmission circuit. So imagine transmission circuit as a spring. The inductance as a spring. And this mass on the two end, imagine them as a big mass. The rotor, turbine, generators, all mass. So it's a dynamic equilibrium at 50 Hertz. Now on that, if there is a sudden change in the power flow, so that mass and spring start oscillating. Like if you have a pendulum with a mass, you just, push the pendulum little bit, touch it, and then, and then you see that it is actually oscillating like that. So this is the oscillation, and this oscillation now have many consequences. What is the consequence? When this oscillation happens, you have the power swing blocking relay that would pick up that oscillation. That is essentially a distance relay zone 3 element, which will be looking at the oscillation. If the oscillations are stable, that it would move across the impedance plane very slowly, and it will be detected as a stable oscillation. So power swing blocking relay will always send a signal that is a stable swing. But if the oscillations are unstable, then the power swing blocking relay will disconnect the line. And once the line is disconnected, then you don't have power flow. So naturally, the receiving end side stop receiving power. Suddenly, you see that couple of thousand megawatts deficit has happened on the receiving end. So then the voltage on the receiving end start dropping, and then all the generators on the receiving end side will have their frequency slowing down, etc., etc. And because this voltage would be dropping, there may be some distance relay in some line, then it will see that again in that distance relay, zone 3, because of this high load, it would encroach, it would enter. And in that load encroachment, then that distance relay will operate. So that line is out. Once that line is out, then another resource is gone. So that way, one by one, you start actually losing your transmission circuit. So you become more and more generation deficit, and load demand is high, voltage is low. So then gradually you lead to the circuit out, and then it can spread if it is not controlled properly. So that is the pathway to blackout. Many blackout has happened historically, starting from 1969 to as recent as even 2025. The blackouts even in Spain in the month of April, that was because of the oscillation in the transmission circuit. You could see that power is megawatt, thousands of megawatt, and there's a very low frequency oscillation about 0.5. So this is the context how we then dampen this oscillation. So dampening of the oscillations can be done through control. So how we that? Okay, so now let's take a look at the time scales of power stream dynamics phenomena. So this we have been talking about rotor angle dynamics. This frequency is 10 to the power of 1 second. So 10 seconds means 1 by 10 is 0.1 hertz. Now if I go here, say 5 seconds, so 1 by 5 is 0.2 hertz. And if I go to 1 second, so 1 by 1 is 1 hertz. So that electromechanical oscillation is in this time scale. Then governor load frequency, then you have the voltage control, then the boiler dynamics. They're all long term dynamics, and also the time is larger, hours. So they're thermodynamic phenomena. But I'm not going to discuss them because I want to focus on the oscillation control. But then you see that there is a stator transient which is about 50 hertz. Then suddenly something has come called inverter based control, which is very fast oscillation. So this is electromechanical phenomena that we are talking about. Now this is electromagnetic wave phenomena that we're talking about. So right now, all converter interfaced power systems will have much larger frequency oscillation. It can be 100 hertz easily. It can be 200 hertz. It can be 8 hertz. So naturally, this modeling, the phasor domain model that we have done all the years, what you see in Kundu's book and also in my book in robust control, there we have assumed that network transient is neglected. So 50 hertz transients are ignored, and then only up to 2 Hz dynamics. So differential algebraic. But with this inverter-based control, we now have larger frequency. So this is the new classification of power system stability that we came with in 2020. So this is the converter-driven stability. This is the electric resonance stability. So slow and fast interactions, and then this is purely electrical, and we can also have the subsynchronous resonance, which involve the multi-stage steam turbine mass. And this is voltage rotor and this. So now we now need to see, so that area need an electromagnetic transient model, and this group of phenomena, phasor domain model, is enough. Recently in the UK, there was 2 oscillations within half an hour, 30 minutes each, lasted for also 30 seconds, 8 Hz. Now, if you look at this oscillation, the oscillations are coming in the kilovolt of the RMS value. So it's a 400 kV circuit, right? It's going up to 430 and to 360. This is not involving any mechanical rotor, okay? It's very strange. And that is expanded. So what are the source of this oscillation? So that is essentially coming from the converter control. So now let's, with this context that oscillation frequency dictate the modeling complexity. If the frequency is less than 2 Hz, we can have a phasor approach. If the frequency is more than 2 Hz, you have to go with the electromagnetic approach, or the EMT approach. So on the phasor approach, so when I started my career as a PhD student in late 90s, so I approached this as a linear robust control problem. So this is my plant. How do I get the plant? So I have input and output, the whole power system model, differential algebraic equation, I linearize them, then I eliminate the algebraic variables, then I get the state matrix ABCD, state matrix A, and then I find the transfer function, which is the output matrix C into Si minus A inverse B plus D. So that is my G. Now this G will vary as the network operating condition varies. That is clear. If the power flow level changes, naturally this also will change. And if the number of circuits change, naturally that also will impact these transfer functions. If the characteristics of the demand changes, that will also impact. So, but if you can pick up the right output signal where you observe the oscillation, like the power flow, right? I was saying, say you have an analog power meter at the substation control room in Bokreshwar, which has got, say, a couple of 500 megawatt. So if that power meter needle is moving like this, so there that oscillation is visible. So that can be your output. And then input is where you can influence this control to be, oscillation to be damped out. Again, within this power generator, you can do that through power system stabilizer, or you can do it through static power compensator, which is sitting in the transmission circuit itself. There are many SBC in Indian network. So you can take a look at that point if there is a good controllability. So once we have a model G, we can get the eigenvalues, and then we see the output matrix C into the right eigenvector for an eigenvalue that gives you the modal observability, and then the input matrix B pre-multiplied by the left eigenvector for a particular eigenvalue that gives you the modal controllability. Now, if you multiply those two, modal observability by modal controllability into modal controllability, you get modal residue. So wherever the residue is high, you will see the peak in the transfer function. So that is where the poles are. So that is controllable as well as observable. So that should be our input output choice. So that is your output Y and input U. So now what are these coming? This is your control, and we need to do this linear reverse control. So there is one setup called mix sensitivity. What it does, it takes, this is your exogenous output. That means any disturbance can be an exogenous input, and any kind of manifestation of this anywhere can be output. So this is essentially a disturbance rejection problem. So I have set this input to be 0. Look, oscillation mitigation is not a tracking problem from control theory perspective. It is a regulation problem because it appears suddenly, and then there is no sustained input to that, and we don't need to track the oscillation. We need to just regulate the oscillation. So that's why the set point R is 0, and this is our exogenous output. So what it does, so there can be a D here, this random disturbance, and then this we call exogenous input, exogenous output. So exogenous output to exogenous input is the mix sensitivity called W1S. Because of this thing, if you just do the matrix manipulation, that will come. And then between Z and U is W2KS, which is called the mix sensitivity that involves the controller. So these two, this one, if we minimize this, you minimize the disturbance rejection. That means minimize the norm, this. And if you minimize this, then you minimize the control effort as well as provide robustness against the uncertainty of the plant. That is operating condition variation, if that uncertainty can be captured as an additive perturbation. Now what you see here, W1S, not by, it's just W1S and W2K, so it's a big matrix. So minimize this H infinity to norm of this matrix subject to some gamma that limit you set. So this is an inequality optimization. It's not an equality optimization because there is a less than equal to gamma. So that's the objective. So that is the setup for mixed sensitivity. There is also other like complementary sensitivity like TS. This is the mixed sensitivity. One can do that. So when we solve this infinity problem and keep this as equality, then the solution can be a point. Analytically, we can solve this as a point. In that, selection of the weight becomes challenging. But if we solve this inequality numerically, because linear matrix inequality, then the solution is inequality. Something less than this means it can be a whole space. So having a solution in this space, having a space for solution is much better than having a point, because the difficulty to get this. And these lines, if this is your eigenplane, like this is the real part of the eigenvalue and this is the imaginary part of the eigenvalue. So these lines are the fixed damping ratio line. So what is this theta? Cos inverse theta into 2, that gives you the damping ratio. So if I have line like this, more damped. If I have line like this, less damped. If I have line very close to the imaginary axis, that is poorly damped. The advantage that the solution is tractable, and also in linear matrix inequality, both frequency domain and time domain objective can be combined. Okay. See, settling time of the oscillation is in the time domain. That you can also do this. Whereas in analytical, only frequency domain. So typically a test system, you have a thyristor control series capacitor, 5-area system. That's a 16 machine 68 bus benchmark system for IEEE task force that was developed. So this is your thyristor control series capacitor in the line. And now we have done the eigenvalue analysis for this 5-area, area 1, area 2, area 3, area 4, area 5. So if you have 5 area, you will have 4 dominant oscillation mode. Why? If you have 2 mass and 1 spring, you have 1 say, frequency of oscillation. So 2 area and connected by 1 line. If we have 3 area, so area 1 to area 2, and then area 1 to area 3, there will be 2 mode. And that means if there are n number of areas, there will be n minus 1 number of mode. This is a 5 area system, there will be 4 mode. We have done the eigenvalue analysis. The one mode is very damped. That has a frequency of 0.79 hertz. All the other mode, like 0.6 hertz, and the other one is 0.5 hertz, and the lowest one is 0.33 hertz, they have very poor damping. And in those hertz, certain area, oscillate with other area. So there is, for any mode, between these 5, there will be 2 coherent area. In one, there can be 3 area, and other can be 2. In one can be 1, and other can be 4. So that is the mode. So that mode, you can see here, this is the damping of that mode 1, 2, and 3, that light blue, and then this also this red, or whatever you call this, and then this light yellow. So these are 3 mode, and if you look at the damping ratio, they are more than 0.1. So that is good. And what is changing? Changing in the power flow between area 1 and area 2, 100 megawatt to 900 megawatt. Why is that? So these are the lines. Area 1 to area 2, if the power flow changes in this line, so the G will change, and that you have designed that control K with additive uncertainty. So that's why robustness is built up. So you see that you have a good damping. Now let's test this for line out. When the line is out between 60, 61, 53, 54, 27, 53. So these are all the line, then bus number between the area. Like 60 in one area, 61 in another area. 61 is here, and 60 is here. Then 27 is area 1, and then 53 is area 2. Okay? And then 54, 53, like this. So between these 2 bars, if some of the circuits are out, what happens to the damping? Now the dampings are again more than 10%. 10% damping for a 0.3 hertz, 0.35 hertz mode means within 5 seconds, your oscillation will settle down. If the frequency is a little bit high, say 0.6 hertz, 10% damping, then with that frequency, the oscillation even will settle even faster. And if we go to 0.6 hertz, 0.5 and then 0.6 hertz, in 0.6 hertz, the high frequency, so it's only a couple of cycles of that oscillation, then you reach the settling time. So higher frequency means every cycle will have actually lower time. So 4 times this time constant would be lower time. So that means with a higher frequency, you can even afford to have a damping of say 0.08, 0.09. But if the frequency of oscillation is say 0.3 or 0.35 hertz, you need to have a damping of 0.2, because for a 0.3 hertz, one cycle is 1 by 0.3, that is 3 seconds. So now 4 into 3 seconds is 10 or 12 seconds. Now, if the specification is that the oscillation must settle within 5 to 10 seconds, so naturally the damping has to be high. Okay, so there is a relation between the damping and the settling time. And this one, you see the type of the load, constant impedance, constant current, constant power. So for different type of load, they are also fine. So then I move to this practicality. How practical is this? When you have single input, single output, this is fine. You can do decentralized. You don't need to bring remote feedback. But if you do the remote local feedback signal may not have the good modal observability. Or if the mode is observable somewhere else, you need to bring that. So that's the problem. So you need to bring in through your communication network. So then it's a centralized approach, remote feedback. Now that signal comes, it takes some time to come because it involves the communication network. And depending on the communication protocol, priority, etc., so that delay. So that delay one can represent, this is the plant again, this is the exogenous input, exogenous output, this is the real input, real output. So then output is reaching the control location with a delay, e to the power of minus sh. So how we approximate this delay? Through Faraday approximation. It will have a right half plane 0 and also another. So when we do that, then the control that you have designed without the delay will be less effective. So that can be handled through predictor approach. If the signal is delayed, you have to predict what would be the value for the control action. So that is called Smith predictor. And that's predictor with this plant, with this ESH, that becomes an augmented plant. And we design the controller for this augmented plant. And then for the real plant, then we absorb the predictor into the controller. So that becomes a real controller. So the problem with this predictor design essentially is very challenging for power network because we have very poorly damped oscillatory mode close to imaginary axis. We also have some eigenvalues which are large negative. Okay. So now if you look at this whole matrix, the computing e to the power of an exponential. So A is a matrix that has got this delay, etc. So it has got
Sir,
large
you are not audible,
eigenvalues.
sir. You are not audible.
Yeah,
sir.
but I'm speaking. I don't know what's happening. As soon as I'm not audible, you just say. I don't know. I mean, I am connected.
Audible.
No, sir. No, sir. You are audible.
Okay. So that this. So then how you compute? So typically, when you do a matrix computation, you have, say, you want to have a orthogonal decomposition, right? Any matrix A can be decomposed as Q into R, okay? Upper triangular into a orthogonal Q. But if that matrix is ill-conditioned, means if the largest eigenvalue to the smallest eigenvalue ratio is high, the condition number is large, so the computation with the matrix becomes numerically unstable or intractable. So here also, when you're doing the matrix computation for the predictor, so this becomes difficult. So then what we have done here, we call unified Smith predictor, where we decompose that matrix into critical and non-critical part. And the non-critical part is by classical Smith predictor. And then the critical part is with modified Smith predictor. Now then we combine them. So essentially one level of transformation of the matrix to do the computation. So then we come with that. But the problem with this infinity-based norm-based control is the order is very, very large. The order of the plant plus order of the weights. So if I have a large power network with say 100 states, so I'll have 100 order controller plus the weights. So 100 to 10 order controller. So that's not acceptable. So we need to go for low order. At the same time, need to have the robustness. Okay, this is the demonstration of this USP-based control, power hardware in the loop. That was 2004-5 Opal T simulations. In 2004, did that. The fault and the response. Okay. So the robust is the parameter uncertainty, model uncertainty, ease of retuning, and industry preference. That's what I said. How we do that? There are many methodologies. I just today talked to you about two. I have done about 5, 6. Eigenvalue, distance minimization, and also simultaneous stabilization, etc., etc. Robust pole placement. So I'll talk about Kharitonov and conic, where they have the advantage that you can include many operating conditions in the design stage. Okay, that means you are incorporating variation of the operating condition in the design stage. So the control that you design, that would be robust, obviously, and this. So what is a Kharitonov? I just made a spelling mistake with Kharitonov on the top. So Kharitonov, okay, let's take a look at this first. This is the plant and the control. What am I saying? Sorry. This is the plant, this is the control. So the plant is output by XS and this, say this BSSS. So if you have plant and control, then if you put together, so then if this has got a polynomial of B by A and it has Y by X, so when you do GK by 1 divided by 1 plus GK, the 1 plus GK also becomes a polynomial. That polynomial will have all these BA and YX. So that polynomial we call as a characteristic polynomial. And ASBS is your plant. Actually, this G is plant. Okay, ASBS plant, and this ASBS are called interval polynomials, and XS, YX are free. Okay, this is the control. Say H is control and G is plant. So this B and A we call interval polynomial. Why? Because this is one operating condition, okay, for G. If the operating condition change, this B also will change, A will also change. So then if I take, say, n number of operating conditions, I will have n number of coefficient for B. N set. And then if that polynomial is of nth order, every coefficient would be changing, or if that polynomial is mth order, every coefficient will be changing for every operating condition. So what you do then, that coefficient, what you do, just observe that what is the minimum value of that coefficient, what is the maximum value of that coefficient. Or all the this BS is a polynomial, it can be nth order, means nth order polynomial will have how many coefficients? N minus 1 coefficient, like 1 plus S, 1 plus B1S plus B2S square plus B3S cube into Bn s to the power of n. Okay, so yeah, Bn number of coefficient. So those coefficient will change always for operating condition change. So one of them will have a minimum value, one of them, and then also other also maximum value depending on two operating conditions. One operating condition will give a minimum limit to that one coefficient. Another operating condition will give you the maximum limit. So that becomes your range, and you call that as an interval polynomial. And keep your control structure fixed. That is XS and YS. That is your controller that you want to do. And then also YS and XS, you can design the order. It can be second order, it can be first order, it can be third order. So that's how the low order is coming in. So now let's see what happens. So let's go up. I just should have flipped the slide. Interval. So when you put that, so that AS, BS, YX, CS, AS into XS plus BS into YS, that becomes an interval polynomial with a minimum and maximum. So what Kharitonov theorem does is it tries to see four Kharitonov polynomial, how it has P0 plus, P1 minus, P2 minus, P3 plus, like this goes from this range, and it constructs this four polynomial. And once this polynomial, if each of those polynomials are stable, then the entire plant is stable for all these operating conditions, because you are considering the range minimum to maximum. So the idea is how you choose Y and X so that you are able to get four Kharitonov polynomial which are stable. And what do you mean by stable? So you have to look at, solve the root and see that roots have a negative real part if they're complex. Okay. So in the Raut-Hurwitz criteria, you know that how to do that. So that is this. So that, how you solve that? This actually transforms to something called bimatrix inequality, where the controller parameters as a Z, XS, YS has got all the coefficients, say this, that ZJ into PIJ, that's the plant coefficient, that AB. So this can be expressed.
भैया अगर रुलाया तो सोच लेना मैं आपको रात को आपके कमरे में दिखूंगी वहां बैठ ले मैं जे लिखवा दूंगी आप बैठ जाओ अम्मा टीवी चलवाई
Okay. So this, see, since you are listening, you can mute your mic. So this delta S, I can finish quickly. This delta S is this, and then stability of this is equivalent to the finding a positive definite Fujara matrix, Hermite Fujara matrix, which is defined by this. That's a maths. Don't need to worry about that. Zj, Zk, Hi. How do I find a matrix which is positive definite? So then it will be stable. So with that, we do this design, and then we see open loop, closed loop. Open loops are very close to imaginary axis. Closed loops are here, 10% damping lines, and so on. And this is the time domain response. Okay. So that was the work that was done by Dumisani. He was from Malai, a South African country, and we published paper on that. Then I come to conic programming, that eigenvalue distance minimization. One way of generalizing a linear optimization problem is to include quadratic cone. So property is a convex, and interior point method is applicable for solution. So if x, if you have a vector x, x1 up to xn, m, if x1 is greater than square sum of this, the other x, so then we call that as a cone. So now let's see if we can cast the control design problem as a cone. If we can do that, then what happens? The cone programming can be solved by convex programming, and that is IP. So it will be easy. So when you apply that convex programming for damping design by way of eigenvalue distance minimization, what do you want? You want your eigenvalues to move from very close to the imaginary axis to an axis where you have a minimum damping. These are the damping lines. So say your eigenvalue, jth eigenvalue is at 0, and you want to move it to j star, lambda j star. So that one you need to move. So the eigenvalue will have a real part. Eigenvalue also will have an imaginary part. And then this eigenvalue, this minimized Tj subject to this. What is that? This is the residue, and this is the plant, and this is the control gain. So normally, if you go to the root locus, the tangent to the root locus. So what is the root locus? Root locus is gk. The gain k into the plant. Now, if I increase the gain slightly, my root locus moves. So, and at every point of the root locus, there is a tangent. So that means for a small incremental change in the gain, that is the direction the root locus is moving. Now, the root locus movement means what? Eigenvalue movement. So then, where I want to move, say if my lambda j star is very close to lambda j0, that is very close, so then I can have that linearity. So that tangent of the root locus is related to the residue of the transfer function rjk, and we put a very small value of the control gain. That's how it is moving, right? So insert a small value of control gain with the residue is related to that. So this is the distance that you are minimizing. The real value of lambda j minus lambda j naught, you are here, you want to be here. So that's the gap. Now that gap is mathematically equal to this residue, real part of the residue times this gain, that into delta xk. So this is our control. So a small value into this residue we get at lambda j0, that's the change we make. If that change is what we want, the lambda j star minus lambda j0, yes. If this is equal to this, that means this is 0. And our then objective would be to minimize this Tj so that we move along the root locus. That's for the real part, and similarly for the imaginary part. And then for a small change, you move the eigenvalue little bit and then add that gain to your controller. And again, small change, again you move. So this is how it works. So this is set for one operating condition for one eigenvalue, okay, and one controller. Now, how it works? Okay, I said that. So how it works for many? So we have NC number of operating condition. We have NA number of poles that we want to move. And then we have, say, NS number of positive stabilizer or damping controller. We can have multiple. So we'll all put together. So then that becomes minimize this subject to this, TCJ should be greater than this. The real part is this, the imaginary part is this. So now in order to then, in order to impose the damping, so then you need to see that this lambda jc minus is equal to minus alpha jc I omega c. So this has to be greater than 0. Then only you are on the left half. And omega jc is tan inverse cos inverse zeta into this. So then these conditions becomes this, like real part is this must be greater than 0, meaning, and then this imaginary part must be less than this. Imaginary part must be less than this, and then this here it should be greater than this. So then this comes out to be the tan theta. So with that moment you include that theta, then you impose a damping line. That means you are moving inside that the damping ratio so that you don't come out. So root locus move like this, and again it comes back towards the imaginary axis, means again you are losing the damping. But if you put this theta constant, damping constant, then you are always moving towards the left. So that is what it works altogether. So that you see that 5% damping line, 10% damping line, 50% damping line. So what happens is, let me see, this should work. Okay. So now I am doing this, that incremental change, because root has to be incremental. Otherwise, the residue relations will not hold good. So you see that open loop poles are moving, you see, and this is my damping line. So iteration after iteration, they move. Okay. So then we see the dynamic response in the time domain. You see that very, very good response. That was done by Rovia, myself, and Nelson. So is it any better approach? Classical design, approach method, rule locus, you have Kundur book, conic programming, tunes controller against using conic. You find all of them here. So we did some comparison. Classical controller, polynomial controller, conic controller, open loop, closed loop, you see that. And then this is their relative performance and so on. And the cost of the control, classic control cost is high, KS is high. Polynomial control is this, conic control is very less. The control cost less means you are not hitting the limit of the actuator, that is PSS, the AVR and fax device and so on. So we have to minimize the control cost. All these things, like I also have simultaneous and robust pole placement, all these things I did not show, but it's all in these books that we wrote, 2 books. So then I moved very quickly to unified modeling. This modeling, how I include the wind farm, which is asynchronous generator with the converter. So that, again, we had a modeling adequacy, simplifications, and broad voltage source converter and multimodular converter dynamic model. And then it suited for frequency and time domain. So typically I can show you this for a 500 megawatt wind plant. So there are 136 wind turbine. The red lines are all those transformer, 680 volt to 33 kV. The blue lines are each of them a kilometer. You know, between the two turbine of 5 megawatt in offshore, there has to be a kilometer of distance. That is this. So if I have 1,000 megawatt power plant in an offshore water, so and it's a square wind field, so I'll have 15 by 15 kilometer by 15 kilometer. So 15 kilometer by 15 kilometer is a lot of distance. When you are flying, you know, over sea where there are offshore wind farm, from the aircraft window, you'll be able to see the whole wind farm, and it will appear to you just like within 2 kilometer or 4 square kilometer, but it is not, because you are so up, say maybe about 15,000, 20,000 feet up. So that appears low, appears very small. That's, you know, if you keep your sight up, so then you see a bigger area. So, but the thing that I want to tell you that there's a lot of cables. That cables has got dynamics, and then it comes to the transformer, and here transformer. Then finally it comes to 155 kV voltage source converter. This side. So, or we do all again operating conditions for linearization and getting the eigenvalue, etc. And you see now there are 4 modes: 310 Hz, 215 Hz, 50 Hz, 10 Hz. So these modes are all more than 2 Hz. So EMT model was the only way. So everything was modeled by EMT. But each of the wind turbine will have about 30 to 40 differential equations, including its control, gearbox, rotor, etc., etc. Okay, turbine, pitch control. So for a 1,000 megawatt wind farm, which is connected to the grid at say 400 kV substation, so that wind farm itself has to be simplified model. So how we do that? We do now model reduction. So this is the wind farm, and this is the converter side where, why? Because the red means this is where this area participate more into this mode. These are less participating. So just then simplify this side and then focus on this side to have this. So we do that model order reductions through again frequency domain tool, singular value decomposition based tool, balanced truncation, source orthogonal decomposition, accelerated directional implicit. These are all the standard, you know, in control theory, and Krylov and so on. Then you could see that in Krylov you are projecting into a low dimensional space. So that you see a model with initial model of 3000 state, it has come to 39 state, almost, you know, 100th. So balanced truncation, full and reduced models are very much matching each other. So that means model reduction is effective and it can be utilized. So then I go to the decentralized dynamic state estimation. Okay, and this is needed for real-time DSA. Knowledge of the whole system model and operating point are not required. Only local measurements are required. It helps design controller for power plants and fact device. What are the process we applied? Kalman filtering. Yeah. We have used the uncentered Kalman filtering by sigma point generation, not extended Kalman filtering, because that requires the Jacobian and linearization. Relative angle, no referencing is needed. We have achieved the robustness through IDFT, that's interpolating this discrete Fourier transform. So the Kalman filtering assumes some the characteristics of this, you know, the signal error characteristics by sigma, that sigma standard deviation. So that as the noise varies, that sigma also will vary. So now Kalman filter, if is provided with actually an adaptive sigma, then that accuracy of the estimation becomes better. And then that feeds the linear quadratic regulator. We call this an extended control design, and that provides the better damping. So the challenge, why we are doing, because slow data update rate, that the packet delay, packet dropout, cyber security issues, robustness issue. So we need to do decentralized, means can we get the dynamics of the network as dominated by the whole network at the interface point of a generator. Okay, so like if we have a phasor measurement unit at the output of say Boxer thermal power plant, so we estimate the dynamics of this thermal power plant and the rest output, that is it is connected to the network and its interface to the network electrically is voltage and its angle, current and its angle. So these four quantity we can measure, and anything happens in the network, so that would be reflected in this voltage and current instantaneously. Okay, but there we assume that the network transients is neglected, that is again low frequency. So then we come to this x dot, this is in the discrete domain, x dot equal to ax plus bu plus something we call pseudo input. What is the pseudo input? Pseudo input is the voltage, theta and current at the interface. That decouple equations the whole the power generator with respect to the network. So this is the additional thing that you are bringing in. And then an optimal control law is found which incorporate cost associated with the pseudo input. So U is your actual input to the control, that is your state, and then this is pseudo input with this G. So now we need to find out this G. This G is this into BI, that pseudo input this. And what is F? F is this. Because this does not involve any pseudo input. F into X. So that is the additional thing we need to put in. And that this G is that. What are the P? P is actually coming from the this thing. That Riccati equation solution. You know, this is an Riccati equation solution. This P and Q come from that. So this control law called extended linear quadratic regulator implemented at each machine using dynamic estimation of states and parameters. So this is your machine, this is your network, machine network. So represent the whole of eastern region, grid in India by this transmission. Now there is only one grid, so you can represent the whole of India grid like this and put every power plant as an interface. So they have PMing. So GPS gives you the timestamp. So this voltage and current, this voltage and current, they're all being sampled at the same time all over the network. So then these as measurements pseudo B theta I phi goes to the estimator and you estimate the state. And then also this also brings the timing, and then you have the control output. It comes to the automatic voltage regulator of the generator and then it does that. So this is this, and you could see that the response very good compared to the centralized wide area damping control, which is more excursion. Decentralized ELQR solid line, which is better. Okay, that and many things we have done with that. They are all in these books for wind as well as this. Yeah, in these two books, monograph. Many they are not books. Research monograph. Not many people have used them. So Abhinav and Linus, they are the people who did. So then I come to the last part of the talk, and I know it's 1 hour, 15 minutes. So then I come to the distribution part. In the distribution system, you don't have any dynamics, but it's a static system, but lots of unsymmetry and unbalance. Quality measurements are there, lack of quality measurements, single phase to two phase laterals, device with discrete controls. These are the challenge. We need to find out some state estimation framework, which is quality consistency biasness that we defined. This is now static state estimation, not dynamic. And then those pseudo measurement, the load, they have multimodal, say Gaussian characteristics, whereas your weighted least square only work on a single unimodal characteristic. So how you do that? So you have to have Gaussian mixture modeling, then merge a different thing and so on. And then we do the estimation, and then after that we do some sensitivity based. When the model is not available, we do some sensitivity based load estimation in first this state estimation, and then we also do some voltage control sensitivity based. Those are the area that we work on with Siemens. So that is in the spectrum power. That while Angshu was introducing me that we worked for this Siemens spectrum power, so that is, it works in this country. And the transmission, robust control, etc. Earlier part it was with the ABB, TCSC Statcom. The wind farm, that model reduction, control, analysis framework was for Darwin-2 wind farm for Alstom grid, which is now GE. The Darwin-2 is a 900 megawatt wind farm in North Sea in Western Europe. So that will work on. So these are all the applications and work. And they are the people. Abhinav was for both. And then Dumisani I mentioned to you. Ravi also I mentioned to you. Nelson for estimation and control. Ravi also there. And also the wind farm reduction was Husni. And wind farm analysis was Linas. Rajat did that unified Smith predictor. Nelson was my collaborator. François developed the unified modeling for synchronous as well as asynchronous, based on which we worked with this Alstom grid. And Ijuddin did the implementation in Siemens because he was the chief product owner in Siemens. So he did many improvisation of that. We just did some basic idea, but if that was 10, he did 90. Then only Siemens accepted it. So it was not mine, actually it is his. And Ravindra was very good in static estimation with less measurements and so on, that Gaussian mixture models and so on. All of his papers, Ravindra's paper, 3 or 4 papers he wrote during his PhD here. Each of them are now cited more than 400. And they are very specific area, still they are very highly cited. This is the current group we have. Right now, actually, I'm in Beijing, I'm with this gentleman and also Dr. Yang, So they are, and last year only from IIT Kanpur, Shumeda joined, Sai Krishna joined. So we have a good group right now. And these are the people who supported me. I stop here and then open for question and answer. 1 hour, 15 minutes. That's how I wanted to do. Stop sharing.
Thank you, sir, for taking us through the insightful journey and providing us the new perspective on power system control. Thank you very much. So participants, if you have any questions, please move ahead.
Okay, I think, yeah, it's there's a lot of things there. So, but I'll leave this slide with you. And this is for FDP. You get some idea. And it's also getting late here, nearly 11:15 Beijing time. I have to wake up early tomorrow for flight and to Hong Kong. So if you don't have any question, then we can conclude, or you need to have a photo again also.
Yes, sir, yes, sir. We have to take one screenshot. Yes, you participants, do you have any question? Please be quick. We have time constraint.
Sir, because sir, this is Viman. I want to know one just a small thing. The control system observability and the power system observability. If you just highlight the similarity and what are the similarity of them. Thank you.
There is nothing like, as far as I understand, there is nothing like control system observability. There is only power system observability. Observability of what? Observability of the phenomena. Now the observability of phenomena is where? It's in the power systems. Phenomena is in the power systems. So you can observe that. Now,
In power system, we come across the terms controllability and observability.
yeah, but controllability is that which input is more influencing that oscillation. Okay, so that's the input U. So that means which power system stabilizer, if I have, will provide more damping to an inter-area mode. There can be 10 generators with 10 power system stabilizer. One of them would be most influential. So that from that point, we are able to control that oscillation. And observability is what is the signal that you need to feed the controller with. That will have the visibility of that oscillation, that is observability. So in which signal your oscillation manifests most? Naturally, it will manifest most in the line power flow because you saw that power flow are oscillating. So line power flow would be a good signal for better modal observability. And then voltage reference of a particular synchronous generator will be good for your modal controllability, or it can also be mainly it will be better if we have a static var compensator in the line where this oscillation is more manifesting. So then the static var compensator voltage reference point has to be modulated. That would then dampen out the oscillation. So that is the modal controllability.
Thank you, sir.
Any further
Oscillation is
question?
an eigenvalue. Oscillation is an eigenvalue. Okay. The eigenvalue will have eigenvectors. Left eigenvectors, right eigenvectors. Multiply the right eigenvectors, pre-multiply by the output matrix C. And you see which output matrix gives you the largest CV, that is modal observability. And multiply that input matrix by the transpose of the left eigenvectors. That gives you the modal controllability, and then see which B gives you the higher value. And their product is residue. So that if you have a larger product, so your control requirement would be less. Because it's like you are able to hit the right input and with the help of a right information. If you are getting a feedback signal which does not show that oscillation at all, so what are you controlling? You cannot control.
Okay. Thank you, sir. Thank you very much.
Sir,
Hello, sir.
Yes.
Hello. Sir, I have one question, sir. So there is any limitation of this controller? So it is applicable for all the kinds of disturbance in the system. There is any limitation?
No. What do you mean by limitation? The disturbance in H infinity norm domain, it is modeled as W1S, W2S infinity norm. Infinity norm means disturbance from any direction, that is your D, exogenous disturbance, and Z, your exogenous output, exogenous input to exogenous output. So H infinity norm always minimize the norm for worst input towards the worst output. But in reality, that is conservative. So then direction has to be, rather than going to infinity, we have to go to also 2 norm optimization. What is 2 norm? The Euclidean norm optimization. If you do that, then what you do, see, oscillation is a manifestation of surplus energy. And that surplus energy in transfer function term, you'll be able to capture well in Euclidean norm, 2 norm. Okay, because the square, if you take any signal, if you take the square, you get the energy, right? So that's the 2 norm. So then people also do mixed sensitivity with infinity norm for something and also H2 norm for the other thing. So now this is one part of your answer, that the disturbance direction, and then the limit is different. Limit is the controller here is coming as an additional input to the automatic voltage regulator or static var compensator. So what is the job of automatic voltage regulator? Is voltage control. What is the job of static var compensator? Is the network voltage control. On top of it, you are modulating the reference point of that. So naturally, the modulation of the reference point, if the reference modulated signal is too high, So naturally the SVC limit would be hit. And also for power system stabilizer, if that modulator signal is high, so Vref for that signal will lead to the hitting the limit of the exciter of the synchronous generator. So that's why you got to be very careful. Maximum plus minus, 10% would be the headroom that should be left for this supplementary damping control. 90% should be utilized for its own primary purpose. That is the voltage control and power flow control, exciter. So that if the control design is not proper, naturally we will hit the limit. So that's how the limit will come into consideration. Actually, these things are not possible to do remote online. I need to have a blackboard. I can draw, I can show, then that will be good. But
Sir,
anyway,
one thing, sir, that is the practical point. One theoretical point of view, it is okay. So from practical point of view, so it can handle any type of problems in the system, any type of disturbance.
Yeah, theoretical point of view, it handles, but
Okay.
theory is not practice,
Right.
After designing all these things, you see that it will still not work. So then still they will retune the PSS.
And sir, another thing, sir. So now the distribution systems are changing.
I need to answer another question, question from another person. So if there are other questions, then I will be able to answer that.
Thank you, sir.
Because if there are no other people to ask questions, then you can carry on asking the question.
Any further question, participants?
Sir, what is the importance of residue in the power system? Residue value.
Residue is everything, Baba. This residue is by definition C times B into
Eigenvalue and residue difference. Sir, sorry for the interruption. Eigenvalue and residue value. What is the difference? Basic difference.
Eigenvalue is the pole, and residue is the product of the controllability times the observability divided by S minus lambda. See, residue divided by S minus lambda, sum of for every pole. How you get a transfer function G? Transfer function GS is sum of, if you have n number of poles, I is equal to 1 to n, Ri divided by S minus lambda I. So add all of them. Ri is the residue for the ith pole. Ith pole means ith eigenvalue. So that how do we do that? It's the product of the modal observability times the modal controllability. Okay, that's the vector product, right? Not the scalar product. So that means residue will come with a magnitude and a phase. So Ri by S minus lambda I sum I is equal to 1 to n is your GS. That's the transfer function definition.
Okay, sir. Thank you, sir.
And wherever you have Ri is high value, so if your S is very close to lambda, so then Ri that way, amplify that. Okay, but if S minus lambda is very small, so denominator is very small, but Ri is also very small, so then that is masking that. So that output and that input combination is masking that pole. Okay, and that input output combination is not good to control that mode if that eigenvalue correspond to that poorly damped mode. So that's why you need to go for a higher value of the residue. And you remember residue times that G times this incremental gain of the control is moving the eigenvalue. Now, if the residue is a good value, a high magnitude, you only need a small gain to move the eigenvalue from the location where you are to where that you want to be. Clear? From that, root locus, if you can remember from that expression. So having a high residue is very, very important.
Thank you, sir, for your very insightful session, sir.
You're welcome.
Any further questions, or we'll close the question and answer session otherwise?
Okay, so the photo.
Okay.
total
Okay,
entire
thank you,
knowledge.
sir, for giving your valuable time. Just we'll proceed for one screenshot. So participants, please switch on your camera.
Are many of you IEEE PS member? Are there any of you who are PS member? Just raise your hand. Anyway, those who are PS member, I want to thank you for supporting me for the election. We'll work together. Yeah, there is a legend. Okay. Yeah, thanks, Pragati, for voting me. India really voted a lot. I'm really grateful to India. More than 850 people out of 1600 voted. The record turnout from India in the history of PS election. So thank you for that.
Okay, done, sir. Thank you.
Okay.
Thank you, everyone.
So, Angshu, may I leave now?
Yes, sir, please. Yes, sir. Thank you once again for
Thank you.
giving your valuable time. Yes, sir. Thank you.
Yeah, I'll send you the slide to Partho or Aniruddha if you need the
Sir,
slide, but it's okay.
Sure,
okay,
sir.
sir. Okay, sir.
Thank you, everyone. So with this, we are concluding the fourth day of the program. Thank you, everyone.
Hello, sir. Hello.
Dr. Naresh Kumar, do you want to say something?